Well, hi guys. I hope you're having a great time at the picnic. What we're going to talk about is how to begin to think about the delta-epsilon proofs in terms of what I call the delta-epsilon game. I didn't make up this term. This is found in a book, I think we have it in the library, called E. McSquared's Calculus Primer. And our goal for today is to be able to find and prove limits of linear functions. So I'm going to begin by a little bit of review, and then we'll get right to it. So far, what we've done is to define the limit statement in an informal and a formal matter. What I'd like for you to do at this time is to pause the recording and see whether or not you can supply the informal and the formal statements. So pause the recording now and go. Welcome back. Hopefully, you should have said that this limit statement means that f of x is arbitrarily close to L for x close to but not equal to C. And less familiar to you, but hopefully you are getting there, you should be able to say that this means that for any epsilon greater than 0, there is a delta greater than 0, such that when x is in the deleted delta neighborhood of C, then f of x is forced to be in the epsilon neighborhood of L. In other words, for every epsilon neighborhood of L, I can find a delta so that x's in the delta neighborhood produce f of x's in the epsilon neighborhood. Now, what I'd like to do today is to talk about how we might use this formal limit in order to prove the formal definition of limit to prove that f of x does indeed have a certain limit L. And our basic plan is going to be this. We're going to use a graph to estimate a limit, and then we're going to use the formal definition to prove that our chosen value, let's call it L, is in fact the limit. In other words, we're going to tighten up a hole that we had last year. Last year we took a look at a graph and said, oh look, the limit looks like it's 4. But if we were honest with ourselves, we were troubled because maybe the limit was 3.999998, and the graph simply didn't show that. So we're going to tighten up that hole. We're going to fill that hole with the formal definition. And for illustrative purposes, we're going to choose the function f of x is equal to 3x plus 1, and we're going to consider the limit as x goes to 2 of 3x plus 1. And when we sketch y equals 3x plus 1, we're very good at those kinds of sketches. We've been doing them for a long time, and we see that we get a straight line that goes here, and it appears that our graph is going to have a limit of 7. And so this is our limit estimate off of the graph. now what I wish to do is to prove that this limit, this value of 7, is in fact the exact limit of the function as x goes to 2. And here's how this is going to work. Let me rewrite the formal definition. For all epsilon greater than 0, there is a delta greater than 0. And in our context, the c that we're talking about is 2, and the limit that we're talking about is 7. So we would say that when x is in the delta neighborhood of 2, then f of x is in the epsilon neighborhood of 7. And so we're going to use this definition in this way. What we're trying to guarantee is that for any epsilon, we can find a delta. We claim that the limit is 7. And so we're going to play a game called the delta-epsilon game. There are 2 players in the delta-epsilon game. First, we begin our first move by claiming that the limit is going to be equal to 7. And now a wild challenger appears. And the challenger says, I don't think that the limit is 7. You don't know that the limit is 7. It might be 6.9998. And so the challenger is going to challenge our claim. The challenger could be a real person, but the challenger could just be our mental conscience asking us, do we really know what we think we know? So the challenger is going to challenge the claim, and so we're going to respond to the challenger like this. Okay, pick an epsilon. Because the challenger is picking an epsilon, he can pick any epsilon. So notice how the game is working out here. The challenger picks any epsilon. And now we are going to find a delta based on that epsilon. We're going to find the delta as a function of that epsilon, such that whenever the x's are within delta of c, then the f of x's are going to be within epsilon of L. In other words, we are going to play the role of there exists a delta. So the challenger picks any epsilon, and then we are going to find a delta. Okay. Now here's the thing. The challenger is going to pick one epsilon, right? And that epsilon, maybe it's 0.1, maybe it's 0.01, is an example. An example is not a proof. So the challenger is free to repeat the process. He's free to say, okay, well, here's another epsilon, 0.0001. And then we have to find yet another delta, so that when x is within delta of c, f of x is within epsilon of L. All right, so how many times do we have to repeat the process? The game is going to end when one of 2 things happens. The game ends when either the challenger finds an epsilon such that there is no delta. If the challenger does that, then he wins, and we conclude that the limit is not L. Or we manage to find a way to prove, to show, that there will always be a delta for every epsilon. In other words, we manage to generalize and in that case, we win. And we get to say that the limit is equal to L. A third thing could happen, and that is that we might not be able to find an epsilon so that there is no delta for sure, But we also might not be able to show that there is a delta for every epsilon. In other words, it may be that the challenger keeps on finding different values of epsilon, examples, and we keep on finding deltas, but we can never agree that there's going to be a delta for every epsilon. And so if we keep on repeating, then the game is a draw. And in that case, we don't know whether the limit is L or not. We strongly suspect it, but we can't prove it. All right. So that's the basic step. The challenger picks an epsilon, we find a delta. Let's see how that works in our particular case here. We were told to evaluate the limit as x goes to 2 of 3x plus 1. We came up with 7 based upon the graph, and now we wish to prove it. And so the challenger makes his first move. By letting epsilon be 0.1. And so what we're going to have to do is to find x's that will, a delta neighborhood, so that the x's in that delta neighborhood are going to force the y's to be within 6.9 and 7.1. At first that might seem like a challenge, but let's actually play around with the algebra and see. So we have to find the delta so that when x minus 2 is less than delta, then f of x minus 7 is less than 0.1. Let's substitute for our f of x. And when we substitute for our f of x, something wonderful happens. And that is that we notice that the resulting expression, 3x minus 6, just happens to be equal to 3 times x minus 2. Now the reason this is wonderful is that the expression x minus 2 right here just happens to match the x minus 2 that we're looking for in our delta neighborhood. So that if I divide both sides by the absolute value of 3, then I get the absolute value of 2 is going to be less than 0.033 repeating. What does this mean? What this means is, since we have some reversible steps here, that if I take x minus 2 to be less than 0.03 repeating, then 3 times x minus 2 will be guaranteed to be less than 0.1. And 3 times x minus 2 is 3x plus 1 minus 7. Aha! We have found a delta. Specifically, delta of 0.1 can be 0.03 repeating. And so now we say, let's reverse those steps. Let delta equal 0.03 repeating, which is equal to 0.1 over 3. And so when 0 is less than x minus 2, which is less than 0.1 over 3, then three times x minus 2 is less than 0.1, and now 3 times x minus, the absolute value of x minus 2 is 3x minus 6. And we can unpack 3x minus 6 as 3x plus 1 minus 7. In other words, for this particular epsilon, we have found a delta so that when x minus 2 is less than delta, then f of x minus 7 is less than epsilon. We win this round of the delta-epsilon game. Not only did we win this round, but we have the beginnings of a strategy to win every round. Because our challenger now comes back and he says, well, you got lucky that time, but let's let epsilon be 0.003. See what you can do with that. And we say, okay, fine. We want 3x plus 1 minus 7 to be less than 0.003. Okay, but 3x plus 1 minus 7 is 3x minus 6. And factoring out, that gives us this, so that the absolute value of x minus 2 is going to be less than 0.001, and hey, we have our delta. If we let delta of epsilon be equal to 0.001, now we can take and reverse all these steps and say, when the absolute value of x is less than 0.001, notice I'm leaving out the deleted part here because it's really not important for our purposes. Then 3 times x minus 2 is less than 0.003, and that's 3x minus 6, which is 3x plus 1 minus 7, which is exactly what we wanted. We managed to find a delta so that when x's are in the delta neighborhood, that forces the f of x's to be in the epsilon neighborhood. We win this round of the game also. The challenger says, wait, what if epsilon, and we cut him off. We say, you know what? I'm going to prove that for any epsilon you can pick, I can always find a delta. Because we've seen the pattern now. We've seen that if whatever epsilon he picks, we can just pick epsilon over 3 as our delta. And let's actually prove that. Let's generalize it. Choose any epsilon greater than 0. Then the absolute value of 3x plus 1 minus 7 will be less than epsilon when x minus 2 is less than epsilon over 3. And so we have found our delta as a function of epsilon. To get to the proof part of it now, we reverse all these steps. We say let delta equal epsilon over 3. Then, let's put the 0 back because we're doing a formal proof now. Then, when x minus 2 is less than an epsilon over 3, that forces 3x minus 6 to be less than epsilon, and 3x minus 6 is f of x minus 7. And so what we have showed is that for any epsilon, we can find a delta, namely epsilon over 3, so that x's in the delta neighborhood produce y's that are in the epsilon neighborhood. And because it is true that for any epsilon there is a delta greater than 0, for any epsilon greater than 0, there's a delta greater than 0, such that this is true, we win the game, and our limit, that's what, try that again. There we go. We win the game, and our limit is proved. That's going to be the spirit of all of this. It's a little bit involved, but I want to review the steps that we are taking here. First, we found the limit. We found a candidate for the limit using a graph or maybe a table of values. Then we took the expression f of x minus L less than epsilon, and we massaged it a little bit until we got to the point where we could find a delta in terms of epsilon such that x minus 2 is less than delta. That gave us the delta that we wanted, and so we reversed all of these steps here to show that when I start off with x minus 2 less than delta, then I get to f of x minus 7 is less than epsilon. That's the way the game is played. If this game seems to you like it's fairly detailed and like you wouldn't want to do it for hard functions, you're exactly right. We are going to play the delta epsilon game only in circumstances where we have no other limit properties, no other limit rules. Currently, we have no limit rules to work with, and so our only option is to play this game. However, we are going to quickly generate a large number of limit properties that will allow us to bypass the delta epsilon process. But in order to prove that those properties work, we're going to have to use delta epsilon on each one. Let's practice with another concrete example, and then I'd like to generalize it to all linear functions. Example 2. The limit as x goes to negative 1, 2x minus 4. I'd like for you to sketch a graph, estimate that limit, probably do it in your head, with some numeric values, and you should get a value of negative 6. And there it is. So our claim is that this limit has a value of negative 6. And we wish to prove that this is so. Rather than doing any numerical values of epsilon, let's see if we can do it generally from the start. Choose any epsilon greater than 0. We want the absolute value of f of x minus negative 6 to be less than epsilon. And since f of x is 2x minus 4, we get this right here. If we simplify, like so, and now we notice that 2x plus 2 just happens to be, the absolute value of 2x plus 2 just happens to be the same as the absolute value of 2 times the absolute value of x plus 1. So that when x plus 1 is less than epsilon over 2, then f of x will be less than, f of x plus 6 will be less than epsilon. And the x plus 1 is exactly x minus c that we were looking for. And so we have found ourselves a delta for any epsilon. Specifically, delta is equal to epsilon over 2. Think of this as our scrap work getting to the delta. Now we're going to reverse it and write the proof. Choose any epsilon greater than 0. Let delta equal epsilon over 2. Then when x minus negative 1 is less than delta, that forces 2 times x minus negative 1 to be less than epsilon. and 2 times x minus negative 1 is the same as 2 times x plus 2, which is the same as, I forgot my f(x), there we go, 2x minus 4 plus 6, so that f of x minus negative 6 is less than epsilon. So when x minus negative 1 is less than delta, then f of x minus negative 6 is less than epsilon, and we win. And we can conclude that the limit as x goes to negative 1 of f of x is in fact negative 6. Now I want to compare and contrast the stuff in red with the stuff in blue. The stuff in blue is our actual proof here. And the stuff in red was what we used to find our delta, but it's really scrap work. And if you see the pattern, then that scrap work is actually not really necessary. We can actually go straight there. The reason that I actually wrote all of this out was that there will be times when we need to play around with the statement about epsilon and work it backwards to find our delta. But in general in life, that might not be the case. And in particular, I think that you see the pattern that we're looking at, and that is this. For linear functions, a suitable value of delta is going to be epsilon divided by the slope of the line, and really the absolute value of that slope. And we can summarize that with our very first theorem, which we will call the linear function property of limits. The linear function property. I claim that the limit as x goes to c of any linear function mx plus b is simply equal to m times c plus b. In other words, I can evaluate the limit for a linear function just by substituting in c for x. And now let's actually do a delta epsilon proof to show that this is so. Choose any epsilon greater than 0. And let delta be epsilon divided by the absolute value of the slope. Then when x minus c is less than delta, which is epsilon over the slope, then that means that the absolute value of the slope times x minus c is going to be less than epsilon. That's multiplying both sides of this inequality by the absolute value of m. We don't need to flip this into the inequality because the absolute value of m is going to be an always non-negative. Well, interesting. What if m is equal to 0? So let's exclude the case where we have a horizontal line, and we'll have to come back to that in just a moment. All right. Carrying on, we get this guy right here. And now what we'd like to do is to show that this is in fact equal to f of x minus mc plus b. But f of x is mx plus b, and mc plus b is what it is. And you can see that that these two are in fact equal to one another. Get that little blip out of there. And so what I have shown is that whenever x minus c is less than delta, that forces f of x minus quantity mc plus b to be less than epsilon, and we win. We have shown that for any epsilon greater than 0, there is a delta greater than 0, namely delta equals epsilon over the absolute value of m, such that when x minus c is less than delta, then f of x minus mc plus b is less than epsilon. And so what we've shown here is that now any linear function can be evaluated really by direct substitution. That's going to be the spirit of things. But we had to exclude m equals 0. What if m equals 0? If m is equal to 0, I cannot choose delta is equal to epsilon over the absolute value of m. So let me come back to the question of a constant function here. If m is equal to 0, then f of x will be equal to a constant b. And from the picture right here, you can see that no matter what epsilon I pick, all of my function values are going to be b. They are going to be in the appropriate epsilon neighborhood. So I can just choose any delta that I want, really, around c, maybe 1. If m is equal to 0, let delta equal 1. Then, when x minus c is less than 1, then f of x minus b is equal to b minus b, because f of x is a constant function, which is equal to 0, and we already know that epsilon is greater than 0. So when x minus c is less than 1, that forces all f of x values to be less than epsilon for any epsilon. And so we conclude, therefore, that the limit as x goes to c of a constant b is just a constant. And we called this the constant rule last year for our limits. And now we see why it works. Well, that's all that I have to say. It is entirely possible that at the end of this video you're going, I wonder about this. So if it's at all puzzling to you, I encourage you to take a second look at it and